This problem, we've got a situation described where we have a 4-foot piece of wire, and someone's going to go in and cut that wire in 2 pieces, and with one piece they're going to make a square, and with the other piece they're going to make a circle. And so we want to know how much wire to use for each of those pieces if we want to maximize, that is, find the largest possible area by adding the 2 areas together of the square and the circle, or if we want the smallest possible area by adding the area of the square and the circle. So let's work the first one. Let's set it up for the first one. We want to maximize area, and we'll call it A. That's our first step. And so we want to build a function around this. And in this case, we're talking about area of a square and area of a circle. So that's s squared plus pi r squared. That's just your general formulas for circles and squares. And so to get this down to a single variable, I'm just going to say, suppose this has a length of x. Let's say we're using that for the square. So what I would need to do is I'd need to bend this thing into 4 little pieces so that each side then would be x over 4. So my area over here would be x over 4 squared. And then the rest of this is going to be used for the circle. Well, what I'm going to do with this then is I'm going to take it and I'm going to bend it into a circle so that the length, which is 4 minus x, the circumference around that circle would have to be 4 minus x. But the circumference of a circle is 2 pi times the radius. So this will give me a way to solve for the radius that's in my formula. I get that the radius is 4 minus x over 2 pi. And so that would go here, pi times 4 minus x over 2 pi squared. That's my radius squared. And this will all simplify a little bit. They'll get x squared over 16 plus, here when I squared, my numerator is going to be 4 minus x squared. The denominator would be 4 pi squared. Canceling one of the pi's, I'm going to get 4 pi. So kind of a messy looking formula, but this would give me the different areas based on whatever x you want to put in here. That makes sense. Obviously my x, excuse me, my x can't be, it could be 0 if you're going to allow me to not create a square, and it could be all the way up to 4 if you're just going to create a single square and no circle. And if that's allowed, then we'll say we've got this continuous function on this closed interval. And so this will be one of those problems where I can find the absolute extrema by finding the endpoints and the critical points and plugging those in and seeing which give me the largest, which give me the smallest. And so actually I can solve both problems at once because I'm going to be able to find the maximum and minimum by doing this. So the endpoints are 0 and 4. And I do have to find the critical points, so I do need the derivative. That's going to be 2x over 16 plus, here I use the chain rule and I get 2 times 4 minus x squared, to the 1. And then the derivative of the inside is minus 1. That's all divided by 4 pi. And I can simplify that a little bit. Let me go ahead and do that before I find the critical point. This is x over 8 plus, over here the 2 cancels, and actually this is minus since I got a minus in there, so minus, I'll have 4 minus x in the numerator and just a 2 pi in the denominator. And so I set that equal to 0 to find the critical point, and what I get here is I'm going to say I get x over 8 equal to 4 minus x over 2 pi. I'll clear out these fractions by multiplying by, I'll need to multiply by 8 pi. And so on this side I get 2 pi, and on this side, actually on this side, multiplying by 8 pi, I'm going to get pi. I'm not sure where the 2 came from. 2 times pi times x, and on this side I get, canceling out here the pi and part of that, I'll get 4 times 4 minus x. So if I clear all this out, I get pi over x equals 16 minus 4x. I'll bring this back over here and I get pi x plus 4x equals 16. I can factor out an x, pi plus 4, and so finally I can get x is 16 over pi plus 4. All right, it's a little messy as far as the numbers go, but I've got my critical point, 16 over pi plus 4. Now, plugging these in to figure out which one's the largest and the smallest, so I can find my absolute extrema. 0 is not too hard to plug in. I get 0, and then I get 4 squared over 4 pi, so that's going to give me 16 over 4 pi, or 4 over pi. And 4 over pi is not too hard to imagine what that's equal to. 4 is bigger than 1, bigger than 3, 3.145. So I mean, this is a little bit bigger. So this is going to be bigger than 1. It ends up being about 1.27 if you use a calculator. And we put the 4 in, that gives me 16 over 16, that's 1. And then putting 4 in here, well, that all cancels out. I mean, it gives you 0 and that's all gone. So this one's just going to give me 1. So that's less than this. And then let's put this last one in. Well, that one's a little bit messy. I'd have to plug in 16 over pi plus 4, square it, divide that by 16, and then plug it in here and subtract it from 4. It turns out, if you stick with it long enough, you end up with the following: 4 over pi plus 4. Believe it or not, it simplifies to something fairly reasonable looking. But if you actually work out what that equals, it's 0.56 approximately. So looking at these, I can see that this is what I would need to do to get the max. So there's an absolute max here. And this is what I would do to get the min, the absolute minimum here. So that says if you want to maximize the area, then it turns out your best bet is just build a circle with the whole wire. Let x be 0. You build the whole wire and you'll maximize that area. If you want to minimize the area, it turns out you should do that. You should chop it off at 16 over pi plus 4, whatever that is. That's about 16 divided by 7-ish, a little bit bigger than 7, right? 3.14. So 16 divided by 7, so it's a little bit bigger than 2. So it says go a little bit past halfway, chop it off, build a square with that part, build a circle with the other part, and it turns out when you put those together, that'll give you the smallest possible area from those two figures. And no other way to do it will give you a smaller area. So that's kind of the idea. We're able to solve both these questions at once: how to maximize the area and how to find the smallest possible area.